ಶುರು ಮಾಡ್ಬೋದು. Yeah, it's ready.
Okay. So, again, good afternoon. Welcome to the last of these courses on phase field modeling. So, this course will actually be quite different from the previous installments, because up to now in the morning I have tortured you with numerous equations. We have done mathematical developments, and I have tried to be as precise as possible to explain you the fundamental concepts of the phase field method. Now, what I want to do is first, I want to talk to you about a few other topics which give you other applications of the phase field method. And I want to indicate you both what have been the progresses and what's the open problems in this field. And I will start out with applications in material science. I will speak to you a little bit about multi-phase solidification, about grain growth, and how eventually to apply this to real materials. Then I will have a small part about the experiments that you have seen in the beginning of the afternoon. I mean, how to describe those physically and how to model this with a phase field model, which brings up the question of hydrodynamics, obviously. And then, if the time is sufficient, I can talk to you about the subject of modeling of liquid crystals, because that brings in some fun with the order parameter, and is an example that the order parameter is not a scalar. Okay? So this is a sort of survey of some things you can do with the phase field method. So there will be also lots of movies, so take this as a little bit as a panorama, sit back, relax, and don't try to understand everything, because it would be difficult to understand everything. And then at the very end, to wrap up, I will try to summarize and sort of systematize the most important points that we have seen during these 5 days, in order to give you the most important take-home messages in the end. Okay, I start out with eutectic solidification. So what is this? Up to now we have seen models for the solidification of a pure substance and for the solidification of a binary alloy, but there was always the coexistence between one liquid and one solid. Now you all know that many materials have eutectic points in their phase diagrams. So here's a schematization, here's again a phase diagram of composition versus temperature, and you see here there is two coexistence between liquid and solid, and there is one specific point here in the phase diagram called the eutectic point, where one liquid can be in contact with two solids. Okay. And you also see that the liquid has a composition that is in between the compositions of the two solids. That means if you solidify a liquid that is located here, you bring it down in temperature. Here you bring it in the two-phase region of the two solids. So the thermodynamic ground state is a mixture of the two solids. And actually what happens is that the system undergoes a cooperative growth mode. That is, the two solids grow together. And why is that? It's because, as I have said, one of the solids is richer in solute, and the other solids is poorer in solute than the liquid. So, in some sense, the poorer solid, it depletes its solid, it rejects it into the liquid, it migrates to the solute-rich solid. In this way, both of the solids profit from each other, and this is the most efficient growth mode. And it results in composite patterns. So there is two pictures here. If we think about directional solidification, that is setup in which there is a hot zone and a cold zone, and we pull the sample from the liquid into the solid state. If this sample is a thin sample, that is a thin layer of liquid enclosed between two glass plates, we can see something like this. So this is a side view, and what you see is we have parallel lamella of two different solids, alpha and beta, that are regularly arranged. This is the lamellar growth mode. This happens when the two volume fractions of the solids are comparable. Otherwise, we can find this, which is the rod morphology. Here, this is a transverse cut, so the growth has taken place in this way. And you see that there are cylinders of the minority phase that are immersed in a matrix of the majority phase. And you can see that here there is a quite distinct triangular lattice that emerges, that is there is a hexagonal order here. Okay, so these are the two most frequent growth morphologies, lamella and rods. Okay, so the first thing that you think about when you think that you want to model this with a phase field type model is that you have a new difficulty because now you have three phases. You have liquid, solid 1, and solid 2. So first of all, you have to go beyond the double well potential that we have always seen because, well, you need 3 minima somehow. Now there have been various ways have been imagined how to do this. There is various ways that work, but actually my favorite way, which is also the one that is most general, is what is called the multi-phase field method. That is, you introduce as many phase fields as there are phases. So in this case, you have one for the alpha phase, one for the beta phase, and one for the liquid. And you see those phase fields in some sense as volume fraction of the phases. So that means that they have to sum to 1. Okay? Of course, since you have this constraint of these 3 variables, there are only 2 that are independent. So I can draw my free energy function as a surface over a 2-dimensional ground space. And here is a plot of the important element of my free energy function. So first of all, here you see something that I call the triple well potential. That is, so you imagine P1 here and P2 there. And you see that the free energy now is a surface that exhibits 3 minima. So obviously the 3 minima correspond to the 3 possible phases. And the black lines here that go from one minima to the other, these are the interface solutions between this phase and that phase. Okay? And we have also seen that if this is a symmetric configuration, it can describe things exactly at the eutectic point. But if we are off eutectic point or at different temperatures, we need to be able to favor one phase over the others. So we need a function that can be added to this one in order to tilt it. And this is plotted here. So this function is exactly 0 on that interface and favors this well. In this case, it would lift up this well with respect to the 2 others, and therefore, for example, favor the 2 solids with respect to the liquid. Okay? Of course, there are 3 such functions, 1 for each phase. Okay? Now, this is an intuitive idea which has been put forward by Ingo Steinbach and co-workers in 1996. But actually, you have to be a bit careful when you do that. And the surfaces that are plotted here come from this big, long paper that I published with my postdoc Roger Fork in 2005. So what's the point? Well, if you consider one of these black lines here, say going from phase 1 to phase 2, okay? In the ideal case, what you would like to have is that P3 is 0 all the way along this interface because it's an interface between phases 1 and 2. And if P3 is 0 all the way, then actually during the interface you have only one non-trivial variable because if P3 is 0, then P1 and P2 are related in this way. So you can eliminate P2 and you get an equation for the interface that can be written in one independent variable. Now if you just pick random functions of the type that I have seen, well, not random, I mean if you just pick any function that has the shapes that I have plotted in the slide before, you will actually get this. That is, P3 will not be 0 all the way along, okay? Because, well, it's easy to see the trajectory of P is determined by the position of the saddle point here. So if the saddle point is not exactly in between the 2 minima, but a little bit off to the right, then you will get something like this. That is, you will get a 1-2 interface that is sort of polluted by the third phase. So that means that the surface tension will be altered and all the calculations will be more difficult. So if you visualize this in the Gibbs simplex that you know well for ternary alloys, and since the sum of the 3 phase fields is equal to 1, I can visualize the phase field configuration also in such a simplex. The ideal interface would correspond to a trajectory where the interface goes exactly along the side of the triangle, whereas the generic trajectory would look like this. Okay? So you have to make sure that you design your functions in such a way that you get this ideal case. Okay? And we have achieved to do that with Roger Folk, and I have just written the polynomial expression here. Don't try to understand them, just you can guess from this that it was not an easy job to find them. Okay? And this has an additional benefit. It turns out that if you consider a system in which phase 3 is absent, so you have only phase 1 and phase 2, this reduces exactly to the quantitative phase field model of single phase solidification that we had before. The model is constructed in that way, so we immediately know that this is a model that has a good thin interface limit, so that we can increase the interface thickness as we want. And this is then proven here by this plot, which is again a plot where I take one pair of lamella, okay? So you have to imagine that this is phase alpha and this is phase beta. I put it in a temperature gradient, so this is the z coordinate. It's also proportional to the temperature. And you see here the 4 color things that you can barely distinguish are 4 simulations with different interface thickness. And the black line is actually a reference simulation done with a different method, the boundary integral method. So you can see with the thickest interface, so where this ratio is the the thickest interface where the interface width is just 1 by 32 times the lamellar spacing lambda. So lambda is the spacing, is the length of one lamellar pair. So the red line is a little bit farther off, the other 3 almost superimpose, and everything is very close to the boundary integral solution. Just for comparison, if you don't pay attention and you just take a model where do not make sure that this blow up of the interface works correctly, then you get this kind of things. You see that all the solutions, the shape looks pretty similar, but they are all at different temperatures. So you clearly see that there is a big difference in performance. And this can be just because you got one of the polynomial terms not right. So there's nothing different in the numerics. It's just if you have, if you do not have that property that the third phase field stays to 0, well, it can pollute all your results, so you have to be careful about that. Well, so now we have a well-calibrated model, so we can have some fun with it. So for example here, this is a directional solidification experiment in which I start from a wild mixture of the 2 solid phases, so red and green are alpha and beta, the liquid is on the top, and just as with the cells yesterday, I will solidify upward and follow the front with my camera. So you see, these little wiggles that go down is actually, this is artifacts of the visualization. So they are immobile in the frame of the material. So you see that this sample is pulled down and the front here goes upward. Ooh, the resolution is not very good here. Well, I think what you can distinguish is that rapidly you have a lamellar pattern, but this lamellar pattern is not very regular. It has a sort of labyrinth structure. Here you can see a bunch of parallel lamella, and I mean the simulation shows you how slowly the pattern orders. For example, here you have a reconnection event, and I don't remember, but somewhere something else should happen. In any case, you see the solidification, the total solidification length is about 20 times the lateral dimensions of the sample. So you can do things on scales that are really interesting for metallurgical applications. And here is another movie where I start from some very thin lamella, green lamella, and you will see that they are immediately unstable. They will decay to rods. But then what's interesting is, so the volume fractions here are determined by the composition of the liquid that is in front of the crystallization front. And what I can do in the simulation is I slowly change that composition. So the volume fraction slowly changes with time. So you will see that the volume fraction of green slowly increases. So first these lamella are unstable, so we form green rods in the red matrix. Now you can observe that the green slowly become thicker and thicker, and then, whoops, everything connects to form lamella. And if I reduce further the red volume fraction here, we form red rods. Okay. So you can watch this movie many times because it's many interesting feature. So for example, here you see these elongated things that are neither rods nor lamella, that you can either understand as broken lamella or as merged rods. Okay, so it's a morphology that has not been catalogued before. But if you look at this picture, this is an experimental cross-section in aluminium copper, I think. Yeah, it's from Trivedi's group. So you see that here you see exactly that same morphologies that are sort of, intermediary between rods and lamella. So I will try to stop this at the right moment. So if you look at this, you will actually see that it has many features that also appear here. For example, this sort of wavy lamella that you can see here, or the elongated rods that are just about to connect. So clearly, the model correctly captures what happens in reality. And now something else also, if you look at the lamellar structure that forms after the reconnection here, you see that it's much more regular than the one that I got from when I started from the random initial state. So visibly, the history of the transformation is important, and if you get a pattern out of a transition, it's going to be much more regular than if I start from random initial condition. The same is true now if you look at the rods that form. You can see there is a sort of propagative instability, and you can see that here, for example, we have a large domain where it's indeed a quite regular hexagonal. So you can clearly see that this kind of models can be used to explore the dynamics of microstructure during solidification in ways that have so far not been possible using just experiments. Now, sort of as a closing remark on that subject, and also as a perspective, I just want quickly to address the question of multi-component and multi-phase solidification, which is of course what you need if you want to address practically relevant materials. Because no practically relevant material is binary, right? And maybe you have 5 or 6 phases. So what's the perspective of being able to do that? Well, the perspective is actually quite good if you take it from the phase field side. Because I have introduced you to the multi-phase field method. I have introduced you to this on the example of 3 phases. But you can extend this to any number of phases. The formalism is the same. You have to use a different free energy functional. For many phases, actually, it's good to use what is called a multi-obstacle functional, and you can ask Abik about all the details of that, because that's what he's using all the time. So this is not that difficult. Then also, of course, if you have a multi-component alloy, that means that you have not only one composition, but you have several. But if you think about it for a while, actually it's quite easy and straightforward to extend the formalism that I have shown to several concentration fields. Because when you have several concentration fields, well, you also have several chemical potentials. But since all this is based on thermodynamics, the thermodynamics of multi-component systems gives you a straightforward path. You have several chemical potentials. You have free energy functions that depend on all these compositions. Quantities like this susceptibility that we introduced are becoming a matrix. Other quantities are becoming a vector, like the concentration fields or the chemical potentials, but everything goes through just the same way, just with a little bit more algebra. So from the point of view of the equations, there is not so much left to do in some sense. All of this has been set up. Even this methodology of the anti-trapping current has been extended already some time ago to multi-component systems. So all the elements that you need are there. So can we now predict all possible industrial alloys? Of course, unfortunately, the answer is no. So why not? Actually, I will be a little bit pretentious in saying, well, the problem is not in the phase field. Because we know how to do that. But you have seen, as I have tried to make it clear, for the phase field metal, we need input parameters. And these input parameters we cannot get from the phase field method, because the phase field method is based on a mean field approximation, so it's not quantitatively accurate. So as input parameter, what do we need? Well, first of all, we need free energy functions. That's still approximately okay, because there is this method called CalFAT, calculation of phase diagram, where people spend years in designing good free energy functions for many alloys. So free energy functions are actually available for many important alloy systems, including ternary ones. Okay. But then, next thing we need is diffusion coefficients. As you all know, generally in alloys, diffusion coefficients are composition dependent. Then if you are in multi-component alloys, you have to worry about cross diffusion, that is the different diffusion gradients that are coupled. And it's really notoriously difficult to determine this in experiments. But if you want to get accurate phase field simulations for a given material, you need this as an input, because you have to put this in the model. And so here you are already on very uncertain ground. Okay. But the worst part is actually that you need interface properties. I have told you, you need as input parameter the interface energy and the interface mobility. Now, even if you are in materials with rough interfaces, so you can say, okay, the interface mobility is just fast, I will set it to infinity. Even the interface energy, there's very little data on that. And especially in multi-component systems, this may also depend on the composition. Not to speak of the anisotropy, we have seen that the anisotropy is very important for dendrites. Nobody knows actually how the anisotropy of the interface varies with composition, for example. There's many hypotheses, but there is no secure data in some sense. So in that sense, we can do many beautiful things with phase field, but actually the results are only as good as the input data. And the input data are not that many. So you have to be aware of that when you want to sell this method for multi-component alloys. If people require that you give them quantitative results, you have to reply, yes, I can do that if you give me quantitative input parameters. Otherwise, I cannot. So it is kind of unfortunate because we cannot solve this ourselves, because we cannot calculate the surface tension with phase field models, but that's the situation. Okay? So this is one point. There is a real need for more accurate input data, especially on diffusion constants and on interface properties. Of course, you can always say, well, this can be calculated with molecular dynamics, but hey, find somebody who calculates the interface energy of 3,000 interfaces with molecular dynamics. Good luck. It's not a nice work, I can understand them, but well, in some sense, this would be needed to go towards a more quantitative simulation. And what we need to do, nevertheless, is, well, as I have showed you, the models that I have presented you, they have been extensively validated in the sense that I have shown you always plots where things have been simulated with various interface thickness, and in several cases there is a reference solution. You cannot tell the same for these multi-component models. There are several on the market in some sense, but the benchmarking in these more complex situations has for the moment not been done very extensively, so we need to check whether these models really hold what they promise. Okay, so that's something we can do and we should do. But in principle, all that is needed to do multi-phase, multi-component certification is there. Okay, there's one line that I have not commented. There's very few systems that are monocrystals. We need to say something about polycrystals. So that's what I'm going to talk to you next. What about polycrystals? Because I have shown you a dendrite, a nice big dendrite in 3D, but this was a monocrystal because the arms were growing in the crystallographic directions. Now real material looks like that. You have several dendrites that grow in different directions, that start to grow, that impinge, and then of course you have a grain structure that may coarsen afterwards. So how can we describe this? Well, the good news is there are models to do that. The bad news is, well, for the moment there is no ideal such model. Okay? Here I've put you some pictures of a paper by Jim Warren, already quite old, but where you can see that indeed all the stages can be reproduced: dendritic growth, impingement, formation of a grain structure, and then well, you don't see it very well, but you can also simulate coarsening with this one. Now, what is the kind of ones that you can use? Again, there are two approaches, the top-down and the bottom-up approach. In the top-down approach, and this was the earliest one that was taken, you just say, okay, you know, people have come up with this multi-phase field method. Normally they say each phase field is a separate phase, but I can also just declare that each grain is described by a separate phase field. So grain 1 is phase field 1, grain 2 is phase field 2, and so on. And since in these models I can specify what is the interaction energy between any two phases, I can also give the grain boundary energies as I want. I can specify them as I want. So what's the disadvantage of this is, well, of course you need to know all the grain boundary energies as a function of misorientation. And also if you want to do a serious grain structure, like say 10,000 grains, you need 10,000 phase fields. Now that sounds heavy. Well, it is heavy. It can be done because actually you don't need all the 10,000 phase fields in the whole space, because in a grain only one is non-trivial, in a grain boundary only two are non-trivial, so you need to take into account trijunctions and quadrijunctions. But the way this works is they have a big matrix in which they store which phase fields are non-trivial in a given space point, and then they solve only for these phase fields. But nevertheless, if you think about the code, it starts to get complicated. Okay, well, so this is phase fields model. Well, sharp interface models, I've already talked to you about this yesterday. They are difficult to handle. Okay, what would be a bottom-up model for this thing? Well, here it's the same picture that you have already seen. Solid liquid interface. Well, of course, the first idea that you can have, well, yeah, I will just do molecular dynamics. I can do a polycrystal. It should be naturally there. It is naturally there. Only the problem with molecular dynamics is you cannot go to large timescales. You are stuck in the nanosecond timescale, so you cannot really describe grain coarsening except on the very, very nanometric scales. For 2 or 3 nanometer grains, maybe you can, but if you want to go beyond, you're too slow. There is a new and quite interesting method for doing this, which is called the phase field crystal method. So, which you can see either as a time-averaged molecular dynamics method or as a simplified density functional method. The way this works, I have put up a picture here. So this is a density field, and you see that this density field exhibits maxima, which are the yellow points, in front of a background, which is sort of the empty space. So you see here, I have a regular structure, and the way this model works is indeed it produces a triangular lattice of maxima, which you can interpret as a hexagonal crystal. Right? And you can also see that there are two different grains because the crystals are oriented like this here and like this here. So the model is invariant by rotation, so you can create grains in any direction you want. And if you start this from a random initial state, you will indeed get a polycrystal, and you will observe grain coarsening. Okay? Only the simulations are also quite heavy because this is a 6th order differential equation, so you can go to somewhat larger lengths and time scales, but still it's not very big. So if you look at this picture, actually the idea that I just want to explain you very quickly now seems to be quite obvious. Because if I want to make a phase field type model, well, we already had the idea that the state of the system should be encoded in the phase field. So the phase field should tell you whether I'm solid or liquid. That's still the case for grains. Now, the grain boundary actually, as you can see here, the grain boundary is a region in state where the order goes down. I mean, it's more disordered than the regular system. It's more ordered than a liquid. So the phase field across the grain boundary should look like this. It should have a dip, right? One is the solid, the liquid would be somewhere here. So a grain boundary corresponds to a little dip in this field. And then I could introduce another variable which just gives me the local crystal orientation at some space point. So an angle that would be like this here and like this there. And so through the grain boundary, this angle should vary like this. This is one orientation, this is the other orientation, and here is the grain boundary. So such models have indeed been set up. They are called orientation for field models. And they are a straightforward extension of the standard phase field model. So there is the normal interface part. Here is the coupling to the thermodynamics for a simple substance. And here is a new part, which is called the orientational free energy. And here is where the difficulties come into play, because it's far from trivial to construct that. I'm not going to go into the details of that because it would require 15 minutes or so. I can go through all the arguments, but the difficulty comes from the fact that, okay, if you're speaking about a phase, you can set up a double well potential because you have two distinct states that are described by phi equals 0 or phi equals 1. Now theta is an orientation, and you have no predetermined favored orientation. So you cannot put a potential in theta, because that would amount to fixing beforehand some crystal orientations in space, which is not allowed. So this potential, this free energy can only depend on the gradient, which means that you cannot use the standard Ginzburg-Landau form, because in the standard Ginzburg-Landau form you need the gradient and a potential. Okay. So the two methods that have been pursued, I thought I had them here. Oh yes, indeed. They are given here. One, for some reasons, you need to include a modulus of the gradient of theta instead of the usual gradient theta square term, okay, which makes the equation somewhat awkward, because in the functional derivative you have to define how to derive a modulus. And the other possibility that actually we have found is that you can use a gradient theta squared, but then you need to use a coupling for function here of the phase field that diverges when you go to the solid. So somehow you always need to put a singularity in the model in order to make it work. But if you do that, it can work. Okay? So the last point is, what are the equations of motion? Well, they are also a straightforward extension of this standard model. You have the Allen-Kahn equation for the phase field. You have the diffusion equation with source term for the temperature or the chemical potential, whatever you like. And for the orientation, we write this simple relaxation equation, so it's another Allen-Kahn equation. Now, actually, everybody involved in the field that has developed these models agrees that this equation is wrong, in the sense that the orientation doesn't just obey a relaxation equation. It has some geometrical constraints that are not respected by this equation. Still, it does a reasonably good job, because it ensures local equilibrium between grain boundaries. It enforces the right local equilibrium law at the trijunction point. So for the moment, nothing better is in sight. So these equations are used. And if you want to see a detailed discussion about what you can do with these models, well, you have the first article in the special edition, where Laszlo Granasi, where it's one of the inventors and protagonists of this type of model, reviews a little bit what you can do with this kind of model on nucleation, right? So I'm not going to go in any more details about that. Just keep in mind that with this kind of model, which is not much more complicated than the normal phase field model, because you still have only 3 coupled equations to solve, this is the type of model with which you can do the simulation that is depicted here. With this, you can put some initial germs with different initial values of theta, and you can simulate the complete dynamics from nucleation and growth until grain growth and coarsening. So this is quite remarkable, actually. Okay, so this was the 2 topics in material science that I wanted to address: multi-phase, multi-component solidification, and the description of polycrystals. So now we are going to step back a little further and say, okay, good, so this was transformation in materials, can I do other things? And here I will come back first to this slide that I showed you the first day. There's many complicated ramified structures, and I will show you now that we can describe some complicated and ramified structures or some other problems that produce such structures, even though they are not phase transitions. Okay. And so and why are we able to describe such phenomena with methods like the phase field method? The reason is that actually they all have a similar origin, because you see here are many different ramified structures. If you want to observe such ramified structures, actually, from a very fundamental physical point of view, you always get ramified structure when you have the interplay between an instability that favors branching, okay, and a stabilizing factor that prevents the branches from getting infinitely fine. Okay. So I will first talk a little bit about the instability. The stabilizing factors I will not go into detail, but I will comment on it. So in all the examples that I have shown on the first slide, actually the instability that creates the branches is what is often called the Laplace instability or the Laplacian instability. So what I have created here is a simple example problem. So I have created a branched aggregate here by whatever process, doesn't matter. So I have created this structure by an aggregation process, and then I have solved the following simple problem. I imagine that this is an electrode. So I imagine that this is made of metal, and I put it to the potential 0, and then I put a ring around, and I put this ring on the potential 1. And then what I do is I just solve the equation for the electric potential between these two electrodes. So one electrode at 0, one electrode at 1. The electric material in between the two. So what do I have to solve? Well, the equation for the potential, as you know, is the Laplace equation. So I have just to solve Laplace of u is equal to 0 with the boundary condition u equals 0 on the electrode and u equals 1 on the ring. Now the colored lines that you see are the level lines of the solution. So they are isopotential lines. And of course, you see that these level lines are crowded around the tips of the structure. Now imagine for a moment that now I let the current flow through this potential distribution. What happens? Well, first of all, you know that the current is proportional to the gradient of the potential. The gradient of the potential is inversely proportional to the distance between the lines, so the gradient of the potential is reinforced at the tip. So the current is stronger at the tip. And in addition, if you follow the current lines which are perpendicular to the isopotential lines, you will see that they bend around and they go to the tip. So the current is concentrated at the tips, which now means that if you have a phenomenon, a growth phenomenon, that needs something that comes to the structure by a flux, you will see that the velocity will be proportional to that flux, and so the tips will grow faster than the rest. So this is a very fundamental phenomenon. This is actually exactly the basis for the functioning of lightning rods. Because if you put a conducting rod up, it will do exactly the same thing, and the lightning, which follows the gradient of the electric field, will preferentially go to this pointed object, and therefore will be attracted to that. That's why this is sometimes called the point effect or the lightning rod effect. Okay? So this is the fundamental explanation why tips grow faster than the rest. And if you think about it, in all these phenomena, the transport equation is mostly the diffusion equation, or it can directly be the Laplace equation, or it can be some hydrodynamic equation. But in some region around the tip, you can always approximate these equations by the Laplace equation. So in all these examples, the tip are created by that same Laplacian instability. Now, what are the stabilizing factors? Well, we have seen the most important one many times in our course, because we have talked a lot about capillarity, and we have seen that capillarity either creates motion by curvature or the Gibbs-Thompson effect. So if you have very strong curvatures, you get a shift of the equilibrium which counteracts this faster growth effect, and in this way you select a characteristic length scale that is driven by the strength of the Laplace effect, which wants to make the structures finer. That's why if you pull harder in the paint experiment, you get finer branches, because you increase the Laplacian forcing. And the capillary effect tries to make the structures bigger, because high curvature is always penalized. Okay, so all these structures result from the balance between Laplacian instability and mostly capillary stabilizing factors. Okay, so let's talk a little bit about this experiment. So this is actually an example of what is called viscous fingering. So here's a little sketch of the cell, just like that is what demonstrated at 2 o'clock. So imagine that you have 2 glass plates and you have a thin space of thickness B there. Now, in the experiments, the finger was driven by lifting up one of the plates. If you want to do this in a little bit more quantitative manner, actually what you should do is you should fix the plate spacing and you should blow in air from one side. Okay? Because actually the plate spacing is very important. So why is this plate spacing very important? Actually, if you want to study this problem, you see it's a hydrodynamic problem, so you would need to solve the hydrodynamic equations in 3D. And actually, since this plate spacing is very small, you can do what is called the lubrication equation. That is, you can separate the scale perpendicular to the plates and the scale within the plane between the plates. The variations within this direction here are very strong, so you can solve that problem separately. And you can put it back into the problem for the other 2 components of the flow vector. And what you find is that you can describe this problem with an effectively 2-dimensional description. So your variable just lives in the plane x and y. And you get a simplification of the hydrodynamic equation, which leads to what is called Darcy's law. That is, the velocity of the fluid locally is just proportional to the pressure gradient within the plane. Okay? In addition, even for the variables within the plane, you have incompressibility condition, so you have that the divergence of the velocity fields are 0. So this Darcy's law, you have this in both phases, but with different viscosities. Okay? And the only remaining piece here is that you have a difference between the pressures in the 2 phases, which is given by the capillary effect, so which is proportional to gamma times kappa. So if you look at this, you might wonder, well, where is the similarity to our crystal growth problem? Well, for this, I invite you, in some sense, to take the divergence of this equation. If you take the divergence of this equation, on the right-hand side here, you will get Laplace of the pressure. Okay. Here, well, you will get the divergence of the velocity, which is 0. So you will get Laplace of pressure is equal to 0. Here's your Laplace equation. And you should remember that in our growth problems, we have solved the diffusion equation. Now, if the time evolution of the diffusion field is slow, then that means that the time derivative is small, which means that this also can be approximated by the Laplace equation. So the transport part is actually almost the same as in our growth problems. This condition is also the same because we had this pressure difference. This was creating the Gibbs-Thompson shift. And the only difference now is that the interface moves not because of a growth phenomenon, not because fluid 2 transforms into fluid 1. It moves because the whole fluid is moving, so it just moves along with the 2 fluids. So there is no separate condition for the interface speed. Okay, so if you do this viscous fingering experiment, what happens? Well, if you do this in what is called Newtonian fluids, that is fluids that have a constant viscosity, So typically, if you put oil here and you blow in air from the left, this is a very long channel. So what you see is, if you start from a flat interface, you destabilize this interface, you get competition between fingers, and then you have one that outgrows all the others, and in the end, you have one single finger growing in the channel. This is called the Safman-Taylor finger, a classical problem in fluid mechanics. So Safman and Taylor, the paper is from 1957 or something like that. It's one of the classic papers in interfacial pattern formation. Now this happens in Newtonian fluids. If you take more complicated fluids, such as shear thinning fluids or normal stress fluids, such as hell gels or polymer solutions, you can see that you can get thinner fingers or thicker fingers or even ramified fingers like this. And if you make things even more complicated, you get a fascinating variety of patterns. So here's the injection of air, this time not from the left side, but from the top in the center of the cell. So here you have a fingering pattern that is radial, and this is done in a liquid crystal. If you bring this liquid crystal through the phase transition from isotropic to nematic, you can get such a pattern. And if you look, oh no, I didn't choose the right one. Because this one has 6 patterns, but 6 main branches, but you can have examples where this has 7 main branches, which of course would be impossible with a crystalline material. So one would like to describe this variety of patterns, and well, I have to tell you, we are not yet come that far, but you can use phase field to do these things, and I will just very quickly explain this to you. So we need an equation for the motion of the phase boundary. So what would we like to do? Well, we would like to write down our favorite phase field equation, which is the Allen-Kahn equation. Now, if we use the Allen-Kahn equation, we have a problem, because I have shown you that if I put a certain droplet of one phase inside the other, it will just shrink. Now, if I have a fluid droplet inside another fluid, it will not do that, because the mass is conserved. So now, there are some people who have imagined how you can nevertheless use the Allen-Kahn equation. That is, they have added this term here, where kappa is the curvature that you can calculate starting from the phase field, and this actually cancels exactly the motion by curvature. Okay, so you can do the asymptotic calculation, and you will see that this actually pushes the interface outward. So it exactly counterbalances the curvature effect. And then the last term here, of course, here the V is the speed of the fluid. So this is just an advection term. So this makes that the interface is transported with the fluid flow. Okay, so if you summarize what this does, the normal velocity of the interface would be equal to minus the curvature of this part. This part cancels that, so in the end only the advection term remains. So what this equation does is it gives you an interface that just stays in place, except if the fluid transports it. Okay? And then once you have this phase field equation, well, you take this into the Hille-Shaw problem. So you take divergence of the velocity 0, you interpolate the velocity between the value in fluid 1 and fluid 2, just as we have had for diffusion coefficients, for free energy functions. You just use the phase field to interpolate, and you put this interpolation in Darcy's law. Here, what you need to do also is to express this capillary force as a function of the phase field. And if you just put the gradient of phi times the curvature, you will get a force that always points inward with the curvature. You take the divergence of this and you do the calculation, and then you can do simulations. So here I show you just some result on a Safman-Taylor finger in a cell of a shear thinning fluid. That is, the viscosity of the fluid actually depends on the local speed. And the red dots here is what you obtain when you have a Newtonian fluid. The black line is the Safman-Taylor theory. So we are not doing too bad, except in this parameter regime. And the blue points are for our shear thinning fluid. And what you can see is the shear thinning effect makes the finger thinner which is indeed what is observed in the experiments I have shown you in the pictures here before, that in shear thinning fluids we get thinner figures. Okay? So with this very simple phase field model, you can treat hydrodynamics. So this is one method. There are several methods to do hydrodynamics. I'm going just to show you a movie for what is called the convective Cahn-Hilliard equation, because you can object to what I have told you before. Well, I shouldn't start from the Allen-Cahn equation, because I know that the Allen-Cahn equation describes a non-conserved variable. The natural equation for describing something that is conserved is the Cahn-Hilliard equation. So, okay, let's do that. Indeed, here is the standard Cahn-Hilliard equation, which you have already all seen. This is the standard diffusion equation, except that here I have added an advection term, okay, with the hydrodynamic velocity here, and then I can couple this to the Navier-Stokes equation. So this is the advected derivative, this is gradient of P, and this term here is new. This actually describes the capillary pressure. Okay, I'm not going to go into detail about this. This is all dates from the beginning of the 20th century. Just believe me, this is the capillary force. And tau here is the friction stress tensor. It's the standard Navier-Stokes equation plus a capillary term. And if you do that, here's a simulation that a colleague of mine has given to me, Didier Jamin from CEA. So he works on nuclear reactors. So I don't want to know what this structure is, but it's a sort of box where on top you have a violet fluid, and then you open a little hole down here, and you will see what happens. So the fluid just flows, and air is filling up the upper compartment, and you see that you can, in this way, actually describe a quite complex fluid dynamics. Okay? So what is plotted here is just the level set of phase field equal to 0. That is what you get from this coupled set of differential equations. Now, can somebody tell me, can somebody see a problem in this simulation? Towards the end especially. Watch closely. Anybody spot a problem? In the beginning, everything seems fine. I'm sure that there is also a problem, but it's not visible. Towards the very end, it's visible. I'll play it once more for you, and then I'm going to tell you. Now we can start watching. Yes. What you see towards the end is some droplets that are floating in the air are just disappearing. Okay. Somebody can guess why this is? Try to remember what we did about what we learned about the Cahn-Hilliard equation. What happens here?
Mass conservation.
Yeah, it's mass conservation, but how is the process called when the small droplets disappear? It's actually coarsening or Ostwald ripening that happens here. It's what we have seen here. If you have two droplets of different sizes, in the Cahn-Hilliard equation, there will be a diffusion flux from the smaller to the bigger one, because the chemical potential is given by this relation here, by the Gibbs-Thompson effect. And it will be higher on the surface of a smaller drop than at the surface of a bigger drop. And so that's what happens here. What happens here. The equation is doing fine thing, but then if a small droplet is in the vicinity of a big droplet, actually it evaporates and the mass condensates on the bigger ones. Now, this is seen in your own eyes a sign of a bad interface thickening behavior. Right? Because if you did this simulation with interfaces that have the physical width, of course this condensation evaporation process should be extremely slow. But here, of course, to be able to do this simulation, Didier was obliged to blow up the interface thickness by a factor 1,000 or 10,000 or what, and visibly this was not done carefully, which means not done carefully in the sense that in this blow-off effect, he completely changed the time scale for this evaporation condensation process so that it's not realistic anymore. Okay? So this is a demonstration that if you just take a simple model and you blow up the interface thickness, you will maybe get artifacts. Okay, so you need to be careful about this. And in hydrodynamics, this science is much less advanced than in solidification. And for me, that's one reason why you should take the modified Allen-Kahn equation, because it doesn't have that problem. It might have other problems, as I've said. Research in this direction is ongoing, and I don't want to be too firm about what's the good model. Okay, now just for fun, here's something else, entirely else. Since 15 years ago, people have started to use phase field model for crack simulations. So in this context, the phase field 0 means broken material, and phase field 1 means intact material. And so what they do is they solve the equations of linear elasticity in the whole material, and then they have an elastic modulus, which is a function of the phase field, which is equal to its physical value in the material and equal to 0 in the crack. Okay? So I don't write down all the equations, they are very similar. There is this usual phase field part, and this time the driving force is the elastic energy. I just show you the movie. So here, you see you have a crack branching process, and you all know when you have to try to smash glass, for example, that cracks branch. So the phase field is capable of describing this. Now these strange gray wiggles that you see are not numerical problems. These are sound waves that are emitted by the crack, because we all know that when something breaks, it's loud because it emits sound waves. So this is all captured by this elastic equation that are solved in the intact media. And one of the biggest advantages, of course, of phase field is that you can easily do simulations in 3D. So here's a few crack simulations of my colleague Hervé Henry, who is a bit of a specialized of doing such simulations in 3D. So here you have a planar crack. So this is you can imagine that you have a slab like this that you rip apart. So it starts out as a single crack, and here it's branching into two lips in some sense. And then all of these fronts destabilize to form a very complicated crack surface in 3 dimensions. Okay, I think I will skip the liquid crystal part because it would be too long. I can maybe just show the final movie. Here's the directional solidification of a nematic liquid crystal in contact with an isotropic phase. Now, what's the difference with the standard solidification behavior? In the liquid, we have an isotropic state. In the solid, we have an orientational ordering. So a liquid crystal is like elongated molecules that have a preferred axis, so to speak. So the little lines here in the yellow part, they indicate what's the preferential orientation of the nematic liquid crystal. And this now grows in this direction, and when you have it grow, it will destabilize and will form a cell. But what happens is this liquid crystal wants to be perpendicular to the surface here, so what is called director field here is distorted, and the model can describe this coupling between the orientation field in the liquid crystal and the interface shape. And just to make a long story very short, how is this done? Well, we have free energy functional that this time doesn't depend on a scalar order parameter, but it depends on a matrix QJK, which is the appropriate Landau order parameter for the nematic to isotropic phase transition. So this is called a Landau-de Gennes free energy. If you want to know where it comes from, de Gennes, Nobel Prize in Physics, has an entire book about the physics of liquid crystals. There you can take this and you can find this. And well, the equations just look the same as for the normal phase field. Just here, now you have to define what's the variational derivative of the free energy with respect to the components of the matrix. And this here is a certain invariant of the matrix that is time. But this is just a sort of matrix generalization of the normal phase field formalism, and you can describe it. Okay, so I think with this, I'm going to wrap up. So what I have tried to do in the last 50 minutes is to give you a small selection of this list. This list is certainly also outdated because it gives you a sort of list of problems that you can do with the help of phase field methods. Maybe most important for you, you can do solid-solid phase transformations. Of course, you all know that in that case, elastic interactions are often very important. But you can incorporate this in a straightforward way in these phase field models because, well, I told you, we need a free energy. And if you have a physical phenomenon, well, you open your Landau-Lifshitz theoretical physics books, where the free energy is listed for a whole host of phenomena. Then you go write it down, you see on what it depends, and you write the corresponding equation of motion for that variable. And you're sure that you're not doing something entirely wrong. Okay? After that, as I have mentioned, you have to be careful about the interface effects. That's the pain and the beauty of phase field simulations. But in principle, you know what to do. Okay? So you can do solid-solid state transformation, drag propagation, and grain gulf I have mentioned. Yes, multi-phase flow I have mentioned. I wanted to say a very innovative area for this kind of simulation methods that I have tried to present you for multi-phase flow is biological structures. For example, there are people who try to simulate the flow of red blood cells in a capillary by the phase field method, because red blood cells are deformable entities, but they cannot be deformed in an arbitrary way because they have a stiff membrane. So you can try to develop phase field method for all these phenomena, and they have in common with the materials, phase field models for materials, that numerically they are relatively easy to handle because they give equations that can be solved in the entire space with relatively simple, regular numerical methods. Okay? So, and of course, in material science, important open question that I have already touched upon at the end of my materials part is we have to connect the phase field world to other length scales in order to advance towards comprehensive materials modeling. I have said we need input parameter. This we cannot get in the phase field world. We need to get it either from the microscopic world by molecular dynamics simulation, or from the macroscopic world by properly designed experiments. So this is what I mean by connection of the length scale. Only if you can connect the phase field world to the lower and higher length scales, you will get a consistent and physically quantitative result. So, I'm almost at the end. I just wanted to sort of, in 3 minutes, do you a little very summary recap of what for me were the most important stations of this course. So we have started by a little recall about statistical thermodynamics. So I have given you some elements of how you can rigorously justify from a microscopic perspective quantities that you already knew from thermodynamics, such as the temperature, the chemical potential, the free energy, and so on. So this is useful precisely because it gives you a handle to do this, to connect length scales. And then we have seen that I have taken very simple microscopic model as an example, that if you have interacting elements, if you have substances that have interactions, well, it's very hard to do exact calculations, but you can always do a mean field approximation. That is, instead of taking into account exactly these interactions, you can take them into account in an averaged way. That is, you calculate the reaction of one element to the field created by the surrounding element. And if you do that, no matter what's your physical situation, you will always end up with the conclusion that the free energy for your system considered is of the Ginzburg-Landau form. That is, it has a local part, which is a potential, which describes you what are the phases that are in competition or in equilibrium. And it has a gradient term, and this gradient term is always related to the interaction between the elements. Okay? So the chemical interactions, the magnetic interactions, or whatsoever, whenever you have short-range interactions, you get this gradient square term. Okay? So it's very general form Ginzburg-Landau function. So this was the first very important step. Okay? A global free energy description for a large range of physical systems. Second very important step, now we have to define the dynamics. That is, we have to define how the system goes to an equilibrium state. And I have shown you that in order to do this, you have to take into account conservation law. If the variable that you have identified to describe your system is non-conserved, then you can write down a very simple relaxation equation, which is called the Allen-Kahn equation, or in mathematical terms, gradient flow of this free energy functional, which will bring your system to a free energy minimum. If your variable has a conservation law, you need to take into account this conservation law because it constrains the ways that your free energy can go down. And the simplest example for such a case we had was the Kahn-Hilliard equation, which describes the phase separation of a binary mixture. So that's one conserved order parameter. So that was the second very important part. We derived the universal form of the equations that conserved and non-conserved order parameters obey. And why is this form universal? It's because we have justified this by thermodynamic arguments, because we have proven in both cases that these equations lead to a decrease of the free energy. And you know from thermodynamics that in a time evolution, free energy always needs to decrease. Second important step. Third important step, we have looked at solidification. And solidification is described by two coupled variables. It is one non-conserved order parameter, which gives you the distinction between the ordered and the disordered state, and one variable that obeys a transport equation. Because interface motion in solidification is always limited by the transport of heat and components. So we have seen how we can consistently write equations for this coupled model of the phase field and the transport equation. And we have analyzed the properties of all these models, non-conserved, conserved, and coupled solidification models, and we have always found the same elements. There are two that are very important. First is the influence of curvature, that is the capillary effect, which in the non-conserved model leads to motion by curvature, application grain coarsening. In the conserved case, leads to the Gibbs-Thompson effect. That means relation between the interface equilibrium and curvature, which is precisely the stabilizing effect of all these branching instabilities. Okay? So these two effects, linear motion by curvature and Gibbs-Thompson effect, are the fundamental bricks that are sort of built in all these models. Okay? Fourth very important part, I have talked to you a lot about the fact that all this is very nice and natural, but to make it a useful tool for simulations, you have to use it with interfaces that are much thicker than the natural interfaces because of the length scales that are involved. So you have to be very careful when you increase the thickness of these interfaces in order to do it in such a way that the physics of these elementary effects, Gibbs-Thompson effect and velocity, stays the same. There are proper ways that are developed for these procedures in solidification. In other problems, things are far less advanced. For example, in hydrodynamics, there are lots of open questions, in fracture as well. So, in some sense, if you want to apply phase field models to a new phenomenon, you have always to go about in two steps. The first step is actually normally very easy, because as I said, you go to Landau-Lifshitz, you look up the free energy, you identify the parameter, and you apply the rules that we have learned. Non-conserved order parameter relaxation, conserved order parameter take into account the appropriate conservation law. You write down the equations, they will be right. Okay? Second step, normally to use them you have to blow up the interface thickness, and there you have to carefully analyze what happens when you do that, which effects get altered, and how you can achieve that you blow up the interface with while preserving the important physical effects you want to take into account. I have given you at least one example where in order to achieve this you have really to modify the equations. This was the example of the anti-trapping current. As I said, this is a term that cannot be justified by the machinery that I have outlined, the thermodynamic machinery and the variational principles that I have introduced. It has to be added by hand to achieve the sort of what I sometimes call renormalizability of the model, that is the fact that you can blow up the interface thickness without altering the behavior of the model at large scales. Okay? And the last message is the material that we have covered in this course is only a very small part of what you can do with phase field models. I have tried to give you a few perspectives on other phenomena that you have described, but I have only touched upon the surface. So there are thousands of papers about things done with the phase field model, so go out and read them all. Of course, you understand that this was a joke, but what I wanted to say is there is a lot of things out there to do, and there is a lot of open question that you can answer with the help of such methods. So I hope that this course has given you some motivation to look out there and maybe try to find some new applications for this phase field. And with this, I thank you all for your attention during these 5 days. And of course, I'm still here to answer your questions if you have. Okay.
Questions?
I killed you all.
Generic questions.
You can
Focus questions.
You can ask questions on all the course that we have had, not only on the session of today.
Yes, morning there are very less questions.
They are tired. There is one.
In the fluid flow simulations you have shown, what is the length scale of how big is the system? And
The
what
brute
was
force simulation, that is, which ones?
regarding the nuclear one application about the fluid flow?
The fluid flow.
Yeah.
Frankly speaking, I don't know. I don't know all the parameters. I just saw him show the movie and I said, oh, that's nice, and so he gave me the movie. But I don't know about the parameters. I'm sorry.
What is the advantage of going in this way compared to the normal way of studying a fluid flow?
Well, it's the same thing as always in free boundary problems. Let me advance a little bit. In the traditional way of doing things, that is, say, in a finite element solver, you would need to describe the surface. This you would need to have a mesh that covers all the surface in order to apply the boundary condition there. For example, that there is a pressure jump between inside and outside. You have to take this into account in order to solve the Navier-Stokes equation. For example, you know that a liquid column is unstable. It will pinch off and become droplets. That's an effect of the capillary pressure. So that means you need to solve for the capillary pressure along the surface of this thing. That is, you need to have a description of the surface, and you need to calculate curvatures. So for this, you need to mesh the surface. Okay. Now your mesh has to describe this surface. And now your mesh has to describe that surface. Good luck if you want to write such a code. I mean, it's years of work with a whole team of developers. Right? The advantage of this is with the Navier-Stokes Kahn-Hilliard equation, if you give me 1 week, I'll do it. With open source tools that are available. Right? I mean, it's not particularly difficult. You download an open source hydrodynamics code, you implement the Kahn-Hilliard equation on top of it, you check it a little bit, in 1 week you get this running. In 3D. If you have a little bit of numerical experience. So that's the big advantage. The disadvantage, of course, that you have, that if you do it this way, well, you get these artifacts. So if you want to get the artifacts out, you have to analyze the model. So here the problem is not numerical, here the problem is physical or analytical. That's precisely why I like this, because I don't want to spend years behind the computer, I want to spend years analyzing equations. I'm a physicist, not a computer scientist or an applied mathematician.
The model for liquid crystals, does the fact that we are using this matrix form for the order parameter, does that lead to interesting effects such as presence of dislocation-like structures in the liquid crystals?
Yes. So you can describe disclinations. Okay. Now this is a whole different talk, but I can just show you one. I can just show you for fun. It's really fun. I can show you one picture. I just need to find it. Okay. Where is this? Okay, it's not here. Here. It's because we did a few simulations for reasons that I don't have the time to explain. We did a few simulations where we were interested, so to speak, in liquid crystal bubbles. So what we were considering is, a sphere that is coated with a thin film of liquid crystal, and in which the director has to be tangential to the surface. So this is called a nematic surface. Actually, I can tell you, well, fiber-covered surfaces play an important role in biology. Okay? So in some sense, you have to solve for this director field on the surface of a sphere. And now comes into play some topology. There is a mathematical theorem that is called the hairy ball theorem. As a joke, that tells you that you cannot cover a sphere with lines without having a defect. Right? You cannot cover the surface of a sphere with all parallel lines. You will necessarily have a problem somewhere. You can immediately see this if you think about the globe. If you look at the meridians, they have two hedgehog points at the North Pole and at the South Pole. And if you look at the longitudes, it's the same. They have a vortex at the North Pole and the South Pole. Okay? So there is a mathematical theorem. There is a topological invariant that is called the Euler number. And the Euler number of a sphere is 2. Here we have a defect in the line pattern, which is called a 1/2 defect, because it's sort of U-shaped. If you look at your fingertips, you can see this. It's basically a line pattern that looks like this. Okay. Homework, all look at your fingertips, you will find those. And these have a topological strength of m equal 1/2. So I don't want to explain it. You can define easily geometrically why you associate this. And to get a topological number of 2, you need to have 4 of those. So you see one here. There's one, the straight line is here, and here's the U. You see the trace of another one here. So indeed, if we look at the sphere from all sides, we find that we get 4. And actually, they are sitting on the corners of a tetrahedron, which is also logical because they repel each other. And the line pattern, what we get is actually what we call the tennis ball configuration. Because if you think of the tennis ball, and if you look at the line that is on the surface of a tennis ball, it describes exactly this configuration. It goes like this, and then comes like here. So it's hard to point out with the finger on the board, but so by minimizing this free energy, where we constrain the liquid crystal on the surface of a sphere, we get what is expected, so to speak, 4 singularities that repel each other and that have a line pattern that is indeed corresponding to an energy minimum for the line pattern at the surface. So this is just to tell you that there is interesting stuff. So this you could maybe still have guessed. What you could not have guessed is if you do the same thing on the surface of an ellipse, then actually one defect is attracted by the tip of the ellipse, because visibly the energy minimum corresponds to the situation where the defect is at the point of highest curvature. Okay? Then you can try to do other things with it. For example, you can have a dendrite that grows out of this. And so this is a dendrite with 4 arms, which you could not get in any crystal. And how this works is precisely at the tip of each branch you have one of these singularities. So there is an interesting coupling there also between topology and growth. Of course, this is complete fantasy, it's just a property of the model. I don't pretend that these things exist, but they are fun. More questions? Yes?
If you have a symmetric crack, so what is the motivation behind this branching of the
A symmetric crack, that's actually quite difficult. So, I'm not really a specialist about crack physics. I can just give you one example why a symmetric crack is not very likely. If you do this, if you have a crack, and suppose that now I pull this one to the left and this one to the right, what happens? The crack goes on like this. It doesn't stay symmetric, it follows the direction of maximal extension, so to speak. Okay? And the crack branching happens when the speed of the crack becomes comparable to the sound speed. So in some sense, it's an interaction of the crack tip with the wave field that it has itself generated. And in that situation, it happens sort of an analogy to that. That is, the compression is not the strongest anymore straight ahead of the tip, but there are 2 regions to the right and to the left where the extension is stronger due to this dynamic interaction, and that's why the crack branches. Okay? But I could not explain you the details, but this is known in the classical crack physics. It's called the Joffe criterion, which tells you that the maximum speed of a crack before it branches is something like 2/3 of the sound speed. Okay. Yes?
Sir, like when we are trying to apply the phase modeling into different fields,
Yes.
So like usually what happens is one phase is actually intermixing with the other. So is there some kind of velocity limitation on how fast these phases are actually intermixing with each other, or how fast one phase is growing in the other phase actually?
What do you mean by intermixing?
It's like, suppose for example, the dendrite is growing inside the liquid.
Yes?
So there, the tip has a velocity, particular
Yes.
velocity with which it is growing outside.
Yes.
So is there a kind of limitation on how fast these can grow so that we can create a stimulation out of this? Or is there like a general thing that we can grow as fast as we want?
Well, no. So, as I have mentioned, maybe no, not as I have mentioned, we have seen when I spoke about this interface scale blow-up that there are certain limits to that procedure because the interface scale needs to be small with respect to other geometric length scales. Similar to that, there is also limitations for the time scales. For example, so, okay. There is one very simple thing. You have the tau dt phi is equal to something, okay? So tau is a sort of relaxation time of the phase field. Now, you see that if your phase field goes from 0 to 1, that means the complete state of the system to go from 0 to 1 is of the order of tau, right? Now, if you have a certain velocity and a certain interface thickness, of course, what you should have is that W over tau, W over V, that is the time that the interface takes to advance by once its thickness, should be much smaller than tau. And should be much bigger than tau. Because otherwise, the phase field cannot follow the geometry, okay? So that means if you fix this relaxation rate, Yes, there is a maximum velocity that you can describe. Because if you go faster than that, then the phase change is too slow to follow the boundary conditions that you impose, so to speak. So indeed, you cannot go arbitrarily fast, because in some sense the phase field has an internal dynamics, and you have to go sufficiently slowly to respect that time scale. Okay? Probably you cannot see anything here.
Read what is on the bottom.
Okay. I think it's an easy concept, because if you add once by once the interface thickness, well, the phase field has to have the necessary time to change its state. So that's where this condition comes in. Okay.
No more questions.
Then let's stop here.
Thanks, Mathis.
That's kind of you.
It's something useful.
Okay. Very good.
Yes, that's why I said it's useful.
Very nice. Maybe I should keep it for my Christmas. For my Christmas trees. Such a nice paper. Make a nice thing under the Christmas tree. Oh, haha.
Use this one.
Yes, okay.
Last time I gave to him a cup.
Good. Mr. Tata, right? Now this is a story because, well, I'm a big tea drinker. So on a normal working day, I will drink at least 5 or 6 cups of tea. So half of the day you see me working around the institute like this. So that's why it's a really useful gift. I will use it and carry it around our institute a lot. Okay? So Mr. Tata will be present in our institute. Okay. Oh. And this feels like a book, huh? I still use your big cup that you gave me, yeah? The big blue one. Now I will have a choice of 2 cups. Ooh, aha, okay, very nice. So tomorrow afternoon I have to go out and find all these balls tonight. You have a very nice campus here, so this will help me to prepare my next visit. Thank you very much. We'll keep the nice bag as well. So now your gifts here.
So,
I apologize in advance for my bad pronunciation of some names. Huh? Okay? Here we have BSK Gargea. What's your real name? Yes, but BSK. Yeah? Your full name. Yogi Tushar Duryodhan Rao. Okay. This is simple. Godwin J. Okay. Here we have Sumya Mishra. Then we have Pramod V.S. Srinivasula. Congratulations. Here we have Pankaj. Pankaj, how do you pronounce this? Pankaj, okay. Here we have Abhijit Ghosh. Abhijit Ghosh. Miral Verma. Congratulations. G. Kamalakshi. Deepu Matthew John. Dasari Mohan. Ayush Suhane. Then we have Bharati Ganesh. GS. Okay. Anupam Raj. Arijit Roy. Abhishek Shandilya. Savya Sachi. Here we have Rupesh R. Chafler. Chafler? I don't know how you, Chafler, how do you pronounce that? Chafler, okay. Sumanta Samal. Sandhi Reddy Hemant Kumar. Ramakrishnan R. Okay. Thank you all for the participation.
Okay, so thank you, Mathis, for conducting this course. Also, Bharti for doing all the stuff, right? Tomorrow we are going to have a mini symposium, right? About 5 talks given by Abhinandan, there's a Funny Kumar who is going to come from IT Madras, there's a Guru Rajan, Mathis, and myself, right? About their research in the recent years. And so whoever is interested, they can participate, right? And it's good that you can also see some of the things that you learned in action, right? So it's going to start at 9:30 tomorrow. We'll have half an hour talks each, followed by a discussion on each of those talks. So yeah, so whoever is interested, just will be there in the lecture theatre from 9:30 onwards. Yeah, most of them will be around, but right. So I mean, whoever is interested, just join. Yep. So with that, we are done with the course. Of course, I mean, we'll be spending about 15 minutes now to get our NIC document.
Okay. Okay. I will see you afterwards. All right. Good job.
Oh, yes.
Yes. So, of course, I'll be around tomorrow, and those who want to ask questions can ask me tomorrow. Right? Or if you find me on the corridors, you can come. Okay. Bye-bye.
So Mathis, where are you waiting?
Or I will come to the office. I can come here. Ah.
Yes, no, he is arranged. I will just find out. Just wait for it.
I'll just give this receipts for them. Abhishek. It's too high for this thing. So, first day he came, that's good. There's a receipt for your Anupam. Arijit. The saree? Pramod? Rupesh? I transfer it to you. Hemant? Suman? Edison? Gururaj? Gargya? Yes. These two charges have already spoken. You can take the remaining balance. 1,200. The SO is also signed. You give this to the guest of the person, the reception whoever is there. Remaining you pay 1,200. They will consider. Okay.
Next, I think. Yes, I will get some rules.